Uh, Good. So I was asked to deliver a summary talk, which is a new experience for me. Just to manage expectations, I will not be presenting kind of any new scientific results in this talk. Instead, I'll be sort of taking many steps back and trying to provide a bird's eye view on what I think we've discussed and what we might hope to accomplish with this meeting and the sorts of problems that many of us in this room are thinking about. So let me start by sort of making the trite but true observation that there's a reason why sort of different eras of civilization are labeled with the materials they use, whether stone or iron or silicon. It's because if we can really understand something new about materials, then this would really have a sort of enormous impact on our society and our civilization. And to that end, what we want is both new ways of understanding materials, ideally in non-destructive fashion, and also new ways of controlling materials and altering their functionality on demand. Yeah, we've made lots of progress sort of towards this over the past 100 years, but most of what's been done over the past 100 years or so has been organized around just a handful of paradigms. So first and foremost, of course, there's sort of thermodynamics and standard equilibrium stat mech, which forms the bedrock of much of our understanding of materials. And then there's linear response theory. Yeah, so it's sort of combination of thermodynamics and linear response, and then built on top of this other structures like Fermi liquid theory and BCS theory that have really guided our understanding of materials over the past 100 years. And the sort of central dogma of these approaches is that we're considering systems which are near equilibrium, and we're considering mostly gentle perturbations of near equilibrium systems and trying to use those to infer some properties. And for the most part, we're working on timescales which are extremely long, so that quantum coherence is not so important. And now the new opportunity, which has opened up in the past decade or so, is really that we, meaning humankind, have acquired the ability to interrogate and manipulate materials optically on timescales which are short enough that quantum coherence really is relevant on experimental timescales. So in some sense, all materials are quantum materials, but now the quantumness is actually important because systems are being probed on timescales which are short compared to the quantum coherent timescale. And also, in principle, we can work away from the linear response regime and also maybe far away from thermal equilibrium. So this opens up new opportunities for characterization and also for control. And I would say, just remind us that that's a big goal that sort of motivates many of us thinking about these sorts of problems. Now, what's been done? Well, fair number of things have been done. So there's been lots of work. A lot of the work has been in somewhat close to equilibrium settings or in settings where there are good quasi-particles, so it's somehow weakly interacting. Even when we're talking about spin liquids, we're sort of starting with some picture where there's spin-ons as fairly sharp excitations. So certainly what analytical work has been done mostly in settings which are either near equilibrium or weakly interacting, at least weakly interacting in disguise. So you go into the right basis for the problem, which maybe is not the free electron basis, and then in the right basis, it becomes a weakly interacting problem. There's also been a fair amount of sort of extensive specific modeling of materials and paradigmatic models. So of course, we're sitting here in what's mecca for detailed numerical modeling of materials. But at the end of the day, if I really put a skeptic's hat on and look at it, then I would say that Rutherford is supposed to have said that all of science is either physics or stamp collecting. And I fear that this particular corner of physics is still largely in a stamp collecting phase, where there's lots of wonderful, beautiful results that we've acquired, but they all seem somewhat sui generis and particular to a single system. And what we really need is new paradigms and new organizing principles that allow us to think about this in some unified and coherent fashion. Now, some themes have been discussed on this workshop. So one recurring theme in this workshop has been multidimensional coherent spectroscopy, now especially two-dimensional coherent spectroscopy. So Peter and Steve both gave these wonderful sort of expository introductions to multidimensional coherent spectroscopy, idea being that you're sort of pumping and probing a system multiple times on quantum coherent timescales and using that to infer information that's not accessible through conventional means. Various examples of this. So Kota taught us or told us how we could use multidimensional spectroscopy to extract properties of Higgs mode couplings in superconductors, both conventional and unconventional, and how you could figure out sort of what the dominant coupling channels for the Higgs mode and superconductors are. Young Beck told us about how we could use two-dimensional coherent spectroscopy to detect various spin liquids, long-standing open problem. Spin liquids are hard to detect with conventional experimental probes, but you can do it with two-dimensional coherent spectroscopy. Oliver told us how you could use 2DCS to characterize properties of spin-ons in sort of spin liquids and how you could use it to read out things like spin-on self-energies. Michele told us how we could use these techniques to infer, for instance, braiding statistics, another famously difficult quantity to access through traditional experimental methods, but maybe you can do it with 2DCS. Eugene told us how we could use this technique to probe Josephson plasmons in cuprate superconductors. Eduardo told us about how we could use them to probe magnon interactions. So there's a lot that we figured out and has been presented in this workshop about sort of clever ways in which the technique of multidimensional coherent spectroscopy could be used to extract information that's not easily accessible through conventional experimental techniques. And that's certainly one, it seems like this is one emerging paradigm for this new field. There's also some open questions which have come up during the workshop. So two that I wanted to highlight. Well, first of all, the basic problem that multidimensional coherent spectroscopy solves in all the talks that were given is essentially that the system has some underlying sharp excitations which are obscured in traditional probes, either by disorder giving rise to inhomogeneous broadening or by some multi-particle continuum effects. And what two-dimensional spectroscopy does for you is it essentially it allows you to extract those sort of underlying sharp excitations from this broadened continuum and sort of read out properties of those underlying sharp excitations. But what if you're in a setting where there are no underlying sharp excitations at all? So there's been lots of discussion in condensed matter physics, for instance, about non-Fermi liquids without any good quasi-particle description. Should we, for instance, expect 2DCS to tell us anything interesting or useful in that sort of context? A separate, interesting open question, and certainly motivated by the talks we've heard over the past, past 2 days, is there a systematic way to go from like here's some physics that we want to be able to probe and experiment to this is the multidimensional coherent spectroscopy experiment that we should do to probe it. So at the moment, it feels to me like a little bit of an art form where you go and compute different nonlinear susceptibilities and hope that one of them has the physics that you're looking for. Now, if there was a way to turn it from an art form into a sort of engineering discipline where, okay, this is the physics we want, this is the thing that we should measure, and actually be able to go systematically from one to the other, that would be wonderful. And it seems at least plausible to hope that we could arrive at an understanding that was this good. Yeah. So that's multidimensional coherent spectroscopy.
Can we comment on this, or should we wait until the end?
You can comment, yeah, by all means.
It seems to me this last point, which is true, I think we all know what to do. We just don't know how to build the lasers to do it. So I think the bottleneck in this latter point is mostly technical. You can find your theorist du jour that tells you, have this, probe that, look at this plot, this spot, look at it. But then there's laser technology.
Like, give an example. What do you mean? Like, I don't get it at all.
I mean, systematic understanding how to go from physics we want to see. Let's say physics we want to see is how phonon A couples to spin wave B or Higgs mode C or something. We can kind of sit together with a cup of coffee, three of us, and say, okay, you got a pump here, probe there, measure this, measure that. Use the LCLS to probe the beam scatter. But we just don't know how to do it technically.
I would maybe even push back even further and say I don't believe we do know how to do it systematically, theoretically even.
Right.
So let's give an example. So Michele told us about how you could measure the existence of the existence of non-trivial braiding statistics. Yeah. And he gave this example in the context of toric code. But suppose we had some other model with, I don't know, Fibonacci annuals. Is there a way to see Fibonacci statistics in multidimensional coherent spectroscopy? I suspect there should be, but I don't know how to do it. Yeah. So like, what's the right nonlinear susceptibility? I mean, in principle, there's an infinite number of nonlinear susceptibilities that you could imagine. What's the right nonlinear susceptibility that would see something like that? I don't know.
Point
that
taken.
seems to-
Point taken. I was just going to say that before you get there, we still don't have the lasers. There's that previous step. Yeah, absolutely. Yeah.
So is that second bullet mostly about theory
Yes.
shortcomings?
I mean, at least
that's how
in my
I
head,
interpreted
this
it.
was about theory shortcomings,
Right.
but Andrea is pointing out there's also experimental technical shortcomings. And point taken. Yeah. Steve.
So, I mean, I would say, I don't quite understand some of these things you just said. It's way above my pay grade, but I would say one thing I noticed is kind of absent from this is discussions of basically the coherence processes, right? And so I've been thinking about it a lot recently because if you look at sort of quantum information people, they tend to work in very simple limits where they assume basically Markovian processes, so Lorentzian lines, and uncorrelated dephasing processes between different members of an ensemble, which for a low density atomic vapor is probably a perfectly reasonable thing to do, but in any solid that's not. Now the thing is that there are some pretty sophisticated understandings of how to do that with generally ultrafast and now multidimensional from the physical chemistry community, because they don't have this separation of time scale. So I think some of this, if we could figure out how it shows up, you might actually be able to look at it.
Correlated noise.
Well, correlated noise, and also just what is the time scale? I mean, so there's a time scale for the dephasing process, and there's memory. And I actually think if you could figure it out, it has a broader impact because people working on quantum error correction and superconducting qubits have realized that. So there was somebody who said to me, non-Markovian behavior is a resource, right? So if we could figure out how some of these processes work in these solids, you could possibly then make a better case that this is a platform that you want to think about using for some of these technologies.
No, I again absolutely agree. This is something you could certainly imagine doing with multidimensional coherent spectroscopy. And by the way, this is meant to be a discussion, not just me preaching to you about what we should be doing. So by all means, feel free to jump in and offer suggestions and things that I've missed. Okay, so multidimensional coherent spectroscopy was certainly one big theme of the past couple of days. A second theme was other nonlinear responses besides 2DCS. So for instance, Professor Shimano told us about how we could probe collective modes and their couplings in conventional and unconventional superconductors using third harmonic generation. Achach told us about how we could use pump probe spectroscopy to probe excitons in Moray systems. Mark Sherwin told us about how we could look at sidebands and use those to infer properties of the Hamiltonian and the wave functions. Dmitry Bazov gave us 3 vignettes on electrodynamics on the nanoscale, and these are all beautiful results. But Nathalie de Leon told us a lot about quantum sensing and how we could leverage nonlinear spectroscopy for powerful quantum sensing. But are all of these different nonlinear spectroscopic techniques, are they all sui generis, or are they part of some broader unifying paradigm, or maybe more than one? I mean, so multidimensional coherent spectroscopy appears to be one paradigm which sort of organized a lot of the talks and stories presented in this conference. Are there others? Yeah, or is each of them just its own thing, completely disconnected from all the other nonlinear spectroscopies? So if there were some unifying paradigms, that would sure be nice. Steve.
So I would actually claim multidimensional is a unifying paradigm because almost all the other techniques you can get from multidimensional. So you do a pump probe, you just integrate the multidimensional one way, you get sort of a spectral resolved pump probe. So all of these, so in some ways, if you really do the full multidimensional, like 3 dimensions, you sort of characterize Chi3, right? And then you should be able to take that and figure out. Now, I'm not saying it's always the best thing to do because it is got a lot of issues, but in some ways you can always look at almost anything else. So I would say in physical chemistry, people don't do simple, they just do multidimensional because it's as good, it contains everything else in it. So.
I mean, does it contain things that are non-perturbative, right? Because it's still sort of at 3rd order or 4th order or something. And like you could have a response that's not Taylor expandable at some.
So that's a little bit tricky because well, yes, we usually interpret it that way, but I think that interpretation is the limitations of our understanding. So first of all, I can show you data where, for example, we push it hard enough, we see the Chi5. And the nice thing about multidimensional is it comes out as a unique peak. So you know you have, whereas if you do another one. Now I would also say the folks looking at, well, making claims about quantum coherence and photosynthesis. I don't know if you know of this whole story, but they basically didn't try to work in the Chi3 limit, and they just did a lot of complicated experiment theory and tried to say, okay, well, this just qualitatively matches what the experiment sees without trying to interpret in a Chi3 limit. So I think in principle, you can do that as well. But probably, yeah, you go to extremely nonlinear things, it doesn't make sense. But you have to be very careful if you do a pump probe well out of Chi3 as well. So
some of the multidimensional is the control of all 3 beams and their time delays and frequencies.
yeah, exactly, and that's what I would say. So I wouldn't say multidimensional. So we like to stay in the Chi3 regime. And so the way we deal with this actually as well is we actually do multidimensional where it's like a pump probe experiment where we come in with a pre-pulse and we hammer it hard and then we do multidimensional. Okay. Now that's a little different because it's definitely not a 3rd order experiment. But the point is the multidimensional sort of you can still interpret in the 3rd order, but in the presence of excitation from a pre-pulse.
I mean, I guess I don't see how you would think of high harmonic generation or high order sideband generation.
That's an extremely nonlinear case. So I would say no, I wouldn't think of that as once you complete, well, again, it depends on the circumstance. As I said, the photosynthesis people did actually work out of a Chi3 in a fairly non-perturbative regime and claimed that they could explain it that way. But you're probing something quite different.
Andre.
So I wanted to go back to the stamp collecting and unifying principles.
Right.
I want to say something a little bit heretical here. I mean, the chemists seem to be very relaxed about not having unifying principles. They have many, many, many problems.
Right.
And they seem to be, building drugs, they save our lives, they do catalysis, they seem to do all sorts of useful things. And they're not so worried about so my question is,
they're not bad people. I just like.
No, I understand, but my question is, the minute we venture into some of these new directions,
right,
should we maybe be a little bit relaxed about stamp collecting and not necessarily look for unifying principles? I mean, I see Peter looking at me like
I agree about the not having.
You're not solving problems.
No.
But I mean, in a sense, maybe we should just kind of. I think just kind of welcome the jungle of this of these experimental.
I don't think stamp collecting as such is a bad thing as such. As you say, chemists come up with useful medicines and like biologists figure things out about immunology and so on.
Andrea, just because it works in practice doesn't mean it works in theory,
But there's also happy theoretical chemists. They seem to have perfectly fulfilling lives, and I mean,
the economists also, have perfectly fulfilling lives.
Okay, I'm being slightly. I'm
getting a little far afield here, but I'm not sure that in chemistry they don't have principles. I mean, there's notions of things like valence that if you really try to define it, kind of doesn't have a crisp idea.
Yeah, except that when they look at molecule A and molecule B and molecule C, these do different things, and they don't really worry about it. They don't just go like, oh, why is my molecule B not the same?
But Andrea, I would
I'm
say,
giving a very broad sort of brush.
I would say if we never find unifying principles, I mean, if that's the way nature is, that's the way nature is. But if they're there, I'd sure like to find them.
Just fine.
Just to go against Andrea, I
Yeah.
think that we have the tendency to criticize chemists, and I think the chemists do have more unifying principles than we do in physics. They're really much better. You say blah, 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 blah of the molecules, but they're able to predict if you do A plus B, what will be C plus D with the rates, and then they're really good in predicting.
Well, that's not what I wasn't disputing this.
But
was
even
not
in
my
the
point.
theory point of view, and they have unifying principles. I mean, you have all the rules that they use to describe how bonds are formed
All right.
or breaking.
Let's continue. So, the third theme
Yeah, I don't know what I'm talking
discussed in this workshop is what I would call coherent control. So, of course, Andrea talked about light-induced superconductivity as sort of classic, like, central example of coherent control. We're actually changing material functionality in some way by shining light on it. Nugadik told us about field-induced magnetization. Paula told us about how we could extend coherence times through driving. So these are all sort of fantastic ways in which we can alter the functionality of materials in some desirable way, induce superconductivity or enhance coherence time or whatever, by driving in some clever way. Again, some open questions. Can we come up with a general, so Nu presented this beautiful understanding of how you could induce magnetization by essentially using light to push on certain modes. Can we come up with some general understanding of what modes you can push on, how to push on them, how to treat this, what this does? Again, can we turn this from sort of stumbling around until you trip over something interesting to like really a systematic science? Maybe a specific example of that could be imagined using a drive to break a symmetry, change the Ginsburg-Landau free energy, induce some new kinds of order. Seems like an interesting direction. Are there general principles for extending coherence times through driving? Again, there's spin echo, there's the Wahuha protocol, and so on. But again, like, are we limited to sort of stumbling around until we trip over like something interesting, or is there some like systematic, sort of unified understanding of how to accomplish these desirable goals, like using optical coherent control? And then the final sort of cluster of talks was to do with theoretical developments. So Michele and Oliver told us about path integral approaches to nonlinear response. Lara told us about diagrammatic approaches to nonlinear terahertz spectroscopy on superconductors. Luca told us about EFT approaches to nonlinear response. So again, there's also sort of theoretical formalisms for dealing with nonlinear response, which are in active development.
I guess one thing I'll jump in there on the theoretical formalism, where what's missing here, and we didn't talk much about, is if you're in some strongly correlated system, actually doing this numerically, where linear response now, to some extent, can be done numerically in a serious way, but it's not clear at all whether any nonlinear thing can be done. You often solve some diagrams numerically, something like that, but actually simulating it fundamentally.
I mean, even analytically in a strongly correlated regime.
Agreed, but I'm just saying, even analytically, you end up doing it computationally, but actually doing direct numerical microscopic simulation seems kind of out of reach for the foreseeable future from the strong correlated regime, at least. So that's it.
So, what did we learn from this workshop? Well, we've learned that nonlinear quantum coherent probes can give dramatic new insights into material properties. There's tantalizing opportunities for quantum control, and that the theoretical tools are just starting to be developed, like, to push away from the weakly interacting near equilibrium regime. Yeah, but there's much that still needs to be done. What we need is, I think, new paradigms analogous to linear response and thermodynamics, things that provide us with a universal perspective that's not specific to any one material or model. And like, probably the only new paradigm that I really see clearly emerging from this workshop is multidimensional coherent spectroscopy. Yeah. Are there others? And there probably are. We could certainly use more than one sort of paradigm for the field. And in particular, I want to emphasize that we want paradigms which are ideally not limited to weakly interacting or near equilibrium settings, and which work even in settings where there's not good sharp resonances, even in the hidden bases. And like this effort is likely to require some sort of integrated attack, which combines experiment, analytic theory, computational theory, and maybe also new tools from many-body dynamics. Yeah, so we're ultimately talking about quantum dynamics in materials, and there's been tremendous developments in many-body quantum dynamics over the past couple of decades, starting with many-body localization, but then also stuff like pre-thermalization and generalized hydrodynamics. And it's certainly interesting to think about whether any of the concepts developed in that setting can be fruitfully applied to the materials context in the sort of quantum coherent non-equilibrium regime. Okay, and I'll conclude with a sort of possible organizational matrix of some things that it might be interesting to do. So the way I organize this was as follows. There's three sorts of things that you could imagine wanting to do. So there's phase characterization. You have some state and you want to figure out what the properties of that state are. There's dynamical characterization. So you want to figure out how the state is going to respond if you push it around a little bit. And then there's full control, where you wanting to induce some desired properties. And you could aspire to do each of these three things, either for gap systems close to a ground state. That's maybe the maximally sort of conceptually simple setting, or for gapless systems near equilibrium, either at zero temperature or non-zero temperature, or finally in a completely far from equilibrium setting. Yeah. So I tried sort of filling in this table, and what the color code means is black text is things which I think there are already experiments that we either heard about or that I know about. Blue text is things where there are concrete theoretical proposals, but I am not yet aware of an experiment. And red text is stuff like, surely there's a way to do this, but I haven't heard it yet. So for instance, over on the left-hand side of this table, Mark told us about how, for instance, you can read out abelian Berry phases from sidebands. We heard about how you could detect deconfinement, how you could measure braiding statistics, all the way over at the other end, the bottom right-hand corner. If you're far from equilibrium and you're trying to do full control, well, actually, I don't even know what to go for here. But there ought to be something that we could put.
Shor's algorithm.
Right, Shor's algorithm, sure. Or doing generic quantum algorithms in materials.
What color would that be?
How what?
What color would that be?
Red.
Surely there's some way.
I think it deserves its own color.
Purple. So, okay, I mean, the entries in this table are by no means an exhaustive list, but in all squares except the bottom right, I at least had some things to put. I don't think I can put something in black in every square, so I don't know if there's anything in black we have to say about gapless systems near equilibrium and phase characterization, or far from equilibrium characterization of dynamical response. But certainly there's much more that could go in each of these boxes. Yeah, this is just some of what has been done already, and sort of filling out the table and coming up with more entries to put in this table. I'd say that's a challenge for the future. Yeah. Okay, that's
question or comment. I tend to think of pump probe spectroscopy as condensed matter way of thinking of quenches, quantum quenches.
Okay.
Is that
What is spectroscopy? I didn't get
pump
it.
probe spectroscopy? Did I think of a pump as a quantum quench when I try to create a density matrix of some, reasonably physical problem, and then see what happens later? Because I kind of feel like, at least in my education, quantum quenches was the first time when you're like, okay, we have to think about non-equilibrium.
I don't think it's quite that, right? And this comes back to what Steve was talking about earlier, because in a sort of AMO quantum quench, you change the Hamiltonian once and then it's just changed, right? Whereas in a pump probe setting, you pump once, but then the system does relax back. And you have to work,
Well, I was going to say, so there's something we didn't discuss in this meeting, but is another, and maybe I should have mentioned it in the intro, but is relevant to this, that there's a group of people that are going and working on some magnet systems where they'll go in and they'll ionize some electrons, which set some crystal field Hamiltonian. And that just gives a discontinuous change to Hamiltonian.
Right.
So you go from being XY to
Right.
for instance, and then they watch spins process and
Right.
something like that. So
So
that's.
that would be really like a quantum quench.
That's a
Yeah.
quantum quench, yeah. And it doesn't last forever, obviously, because things want to go back, but it lasts, long enough that
Right.
it's interesting. So that's a,
Well, there are
That's an
shallow
interesting-
quenches and there are hard quenches. I feel like linear response is like a very shallow quench. Oh, Steve.
So I see you have hot electron relaxation up there. There's actually been quite a bit of work on that in semiconductors.
Okay,
There's even a whole conference.
so
on
that should be in black.
That should be in black, and there's
Okay.
been a little bit of work on metals as well, of like in gold exciting and doing. So there are some, I think there may be a lot more. It was an old topic that kind of died out, so I think it's potentially something that there's probably something new to do, but it is something people look at.
Eugene?
Response to Vadim's question, I don't think that pump probe can be reduced to quenches. Actually, Andrea told us about an example where pump excited phonon modes, and that turned the system into a Flaquier system. And therefore, to understand properties like, say, cusps in reflectivity that were obtained, you could not get it from some renormalized Hamiltonian. You actually had to think about it as now a Flaquier system, but an interacting Flaquier system. And this type of kind of pump as inducing interesting time-dependent state by exciting collective modes, to me seems a kind of like a very common thing. That there are phenomena which you simply cannot understand from the perspective of free energy landscape, some kind of transient quasi-equilibrium state, but you should really think about inducing some dynamical state. And this actually makes bridges to other fields, like say in optics, there is a community who work on time crystals, like photonic time crystals. It's not time crystals that we're used to. These are people who want to change index of refraction on the time scales comparable to the period of optical oscillations. And when they do it at optical frequencies, it's very hard. Terahertz, it's very natural. You excite the collective mode and it sort of oscillates on the same frequency as you're probing. So maybe we can also, maybe it's, I could detract it, but we can also say that what we learned during this conference is that condensed theory should learn nonlinear optics.
Yes.
So quite a few phenomena
Absolutely.
turn out to be like kind of people have thought in a different context.
Thank you. I gave up on that years ago.
Well, but maybe this is an idea whose time has finally come.
Yeah, I have to say, I am so thrilled by the existence of this workshop and that we have theorists such as yourself and all the theorists here who are really thinking seriously about these problems. And just to follow up on Steve's comment about hot electron relaxation, yeah, I mean, there's a huge literature on that. I think it wouldn't be, I don't think it's completely understood, and I think it wouldn't be a bad thing if, some people in this community, a theoretical community.
we have one paper on striding Rutheniate, so strongly interacting for liquid, so far, so it's something works.
Yeah.
I guess there's one color code that's missing, which maybe would be also interesting to see, is that you've got color codes for experiment exists and claiming that things are understood. You've got things that theory proposal exists. How do you do the experiment? Nothing exists. What about the experiments that are still mysteries? There must be some of those, and those are often the most interesting. You don't have a color code for that. What is the kind of catalog of unexplained horrors?
Yeah.
That we should be looking at explain.
Yeah, I don't know what those are, but yeah, there should be a color code for that.
Yeah, you have to ask us.
But I think that's an equally important thing. It's not just coming up with theory proposals, right? Other things where coming with a different lens is useful.
the
Like,
puzzles.
that's an important question. The puzzles are as important as the kind of, instruction manual.
Well, I think one of the puzzles is how do we think about dissipation and decoherence and dephasing in systems that are very far from thermal equilibrium, because the sort of canonical way people think about it is, as Steve was saying, is, well, you think of a sort of an isolated qubit that's weakly interacting with its environment. There's T1 and T2, but there's much more to it.